Let's now look at an analytic example of how do we calculate the magnitude and the phase if we know the transfer function. And this is going to commonly be the case in this course. We already are going to do the modeling and have a transfer function. So in this example, let's look at this simple transfer function, this first order transfer function 1 over s plus 10. So as we saw previously, we are going to be finding the absolute value or the magnitude of this and the angle of this, but not of g of s, g of j omega. So I'm going to put j omega in for s and do a little bit of algebra here. So replacing the s with the j omega, I'm going to flip the order of the 10 and the j omega just so algebraically it looks a little bit easier to work with. Now, a standard thing we do with algebra is we don't like imaginary numbers in the denominator. So I'm going to take this fraction, I'm going to multiply the top and the bottom by the complex conjugate of the denominator. So 10 minus j omega, 10 minus j omega, multiply the top and bottom. So I've just rearranged this g of j omega to be 10 minus j omega over 10 squared plus omega squared. I've not changed anything. I've multiplied it by 1. I just want to express it with my complex number in the numerator rather than the denominator. And we'll see how this is beneficial in the next step. The first thing I want to look at is what's the relationship between the magnitude and the frequency for this particular transfer function. So to find the magnitude as a function of omega, I need to find the absolute value or the magnitude of g j omega. Well, I have g j omega now, and I have it expressed in this way with the complex number on top. So let's see how we can find the magnitude. Right, so as I said, the magnitude is just its absolute value or its magnitude. And for complex numbers, we can find the absolute value by taking our number or our function, so g of j omega, and we can multiply it by its complex conjugate. So that's what this g bar is. And then we're going to take the square root of it. And we can also do this with real numbers. It's just that in a real number, it's its own complex conjugate. So let's say we had the real number -2, and we want to know its absolute value. Well, it would be -2 times the complex conjugate of -2, which is also -2, so that would be +4, and I take the square root of that, and I get 2. So for real numbers, it's simple. For complex numbers, we need to use this definition. So coming over here, I can take, again, that g j omega, which is going to be, I kind of split up a little bit here. I have the 10 minus j omega here from g. I have g conjugate, which gives me, when I do the conjugate, I replace the negative j with a positive j or vice versa. So from g bar, that's where this 10 plus j omega is coming from. And I have a 10 squared plus omega squared times another 10 squared plus omega squared in the denominator because that hasn't changed between g and g bar. So that's where here this quantity 1 over 10 squared plus omega squared is coming from. Now I can just FOIL this out, the 10 minus j omega, 10 plus j omega, and I'm going to have some simplification happening. So in the end, skipping a little bit of the algebra, I'm going to get that the absolute value of g, or the magnitude, is 1 over the square root of 10 squared plus omega squared. So again, take note that this magnitude that we're going to be applying in a minute here, the ratio of the output amplitude to the input amplitude, that b over a from the previous slides, is a function of omega. So the value of m changes, the value of that ratio changes depending on what omega is, as we see on the right-hand side here. So now analytically, we have the magnitude as a function of omega. We're going to put that aside for a moment. We want to find the phase. So by definition, that phase phi, we want to find the angle of g of j omega. Now, how do we find the angle of a value here? Is going to be, since g is a complex number, a complex value, coming back up here, the angle is just going to be the, we can use the arctangent of the imaginary part over the real part. So if we see here, the imaginary part of this is, if I won't include the j in it, but the imaginary part is this omega over 10 squared plus omega squared. And there's a negative out in front, so negative omega over 10 squared plus omega squared. Coming down here, we see that's the numerator in this fraction. So negative omega over 10 squared plus omega squared. And then I divide it here by the real part. So coming back up to my definition of g, the real part of this is just the 10 over 10 squared plus omega squared. So I'm just taking this portion and putting that in the denominator of this transfer function. Okay, so I do some algebraic simplifications. The 10 squared plus omega squareds are going to cancel. So I'm left with over here negative omega over 10, the arctangent of negative omega over 10. Notice here one thing, I'm using the subscript 2 with the tangent, or more with the arctangent. This is saying that I want to use the 4-quadrant arctangent. Now normally, if we take the arctangent of a number, it is just going to give us a value between negative 90 and positive 90. So it only covers half of the angles it could be. What the 4-quadrant arctangent does, it's going to give us a value between negative 180 and positive 180, or depending on the calculator, maybe 0 to 360. But regardless, it gives us the full 360-degree angle. Because with the 4-quadrant arctangent, we're going to take into account is the negative sign on the top, the numerator, or the denominator, or instead of just saying, oh, there's a negative on top and negative on bottom, that means it's positive, it says, oh, it's negative on top and negative on the bottom. So what it looks at here is, for example, if we have a negative numerator and a positive denominator, that tells us the y value is negative but the x value is positive, that should be in quadrant 4. If the numerator is positive and the denominator is positive, then we should be in quadrant 1. If the numerator is positive but the denominator is negative, we should be in quadrant 2. And actually, if they're both negative, then we should be in quadrant 3. So for this particular example, we see that since the numerator is the only thing that could be negative, this will always be in the same quadrant. But in general, that's not going to be the case. So we'll see in MATLAB how we can use the 4-quadrant arctan rather than just the normal arctan. So what does all this mean? We have the magnitude as a function of omega. We now have our phase, or phi, as a function of omega. What can we do with it? All right, so just copying what we had before. For this analytic step, we're just going to look at kind of some extremes. What happens to the magnitude and the phase under two different conditions? And then we'll test this a little bit later when we numerically look at the magnitude and the phase and see that they do agree with each other. So let's see what happens in the case where our input has a low frequency. So that is to say that omega is very small, it's approaching 0. What's going to happen to these values? So if we look at the magnitude here, as omega approaches 0, we can really just put in the 0 here for omega. That's fine. We're not dividing by 0. We don't have 0 over 0. So the limit is going to be easy enough to apply here. So we're going to see that we just have 1 over the square root of 10 squared, which is just going to be 1 over 10. So as the input frequency gets smaller and smaller, then the magnitude is going to approach 1/10. And again, that magnitude is the ratio of our output to our input. So the output will be 1/10 of our input for very low frequencies. And what happens to our phase? So if we see here, we have the arctangent. If we put 0 up at top, we're going to be taking the arctangent of 0, which is going to be 0 degrees. Remember, the arctangent more or less undoes the tangent. So if we take the tangent of 0, we get 0. So for low frequency inputs, our phase is going to be 0. Again, I'll define the phase in a little bit here, a little bit better, and our magnitude is going to go to 1 over 10. So what happens if our frequency is much greater than 0, if it starts to get very large? So again, analytically, what we can look at is, let's look at the magnitude first. If we have a very large frequency, so this is meant to imply it's, I guess, going towards infinity, it's getting very big. If we look at m, when omega is really big, we're adding a 10 squared to it. So what we can say is that the omega is much larger than the 10 squared. The 10 squared is basically not going to make a difference anymore. So this is going to go for very large values of omega. It's going to go to 1 over the square root of omega squared, which is just going to be 1 over omega. Right? So for large values, for large input frequencies, that magnitude is going to approach 1 over omega. So as omega gets larger, that magnitude is going to get smaller and smaller. And let's look at what happens to phi. So here, if omega is very large, we're going to like negative infinity. We want to take the arctangent of negative infinity. Well, if we think back, when we took the, basically this is going to be when is the tangent undefined. So it's undefined at, well, two places. It's undefined at negative 90 and it's undefined at positive 90. But here, if we try to take the tangent of negative 90, it will say undefined, but it's because it's more or less saying it's like negative 1 over 0. So it's a very large negative number. However, if this were positive, we would get positive 90 because the tangent of positive 90, again, it's undefined, but really it's going towards a very large positive number. So what this is telling us is for large, high frequency inputs, the magnitude is going to get very, very small. So the output amplitude gets very, very small for high input frequencies, and the phase is going to go to negative 90 degrees. Now we didn't look at what happens in between or for any arbitrary value of omega. Now we could compute it because these are just equations that we can get values for m and values for phi. But we're going to do that numerically for this course. But again, we can do it analytically. I just wanted to look here at what happens in these extreme cases, a very low input frequency and a very high input frequency. What happens to the magnitude, what happens to the phase, and again, we're going to confirm this in a couple of slides here. But I want to talk a tiny bit more about phase because it's a little bit, I still haven't really defined what it is. So we can have a phase lead, and for this definition of how we're putting the output together, that's going to be a phi value that is positive, or a phase lag, which is going to be a negative phi value. But really what it's telling us is what fraction of a forcing cycle, so what fraction of a full period of our input is the offset, is the output offset from the input. So what we can look at here is typically our phi is going to be in radians. So we can divide it by 2 pi and we get a fraction. So it might be like a quarter or a half or 3/4, 2/3, whatever it is. That tells us again how much we are offset, the output is offset by the input. So for example here, if we get a phi of 0 or a phase of 0 degrees or 0 radians, then the output cycle matches the input cycle. There is no lag. What this is telling us is the time when we have a peak in the output matches the times when we have peak in the input. And we call this being in phase if the phase is 0 degrees. When the peaks match and the troughs match, we are in phase. Another example, let's say our phase is negative 120 degrees. Well, if we put it up in here, negative 120 over 360 is negative 1/3. The negative, again, tells us that we are lagging. So the way we can interpret this is that our output will lag by about 1/3 of a cycle, the input. So our peak on the output is going to be about 1/3 of a cycle after the input peak. And the same thing with the valleys or the troughs. And a final example here, let's say our phase is negative 180, then our phase comes out to negative 1/2, or we're going to be 1/2 cycle behind. So again, negative 180 over 360 is negative 1/2. We are lagging by 1/2 of a cycle. So what this is going to look like in our output is that a peak in our output matches a valley in our input. A valley in the output is going to match a valley in a peak in the input. So we have valleys in the output where we have peaks in the input and vice versa. And specifically here, when it's exactly a 1/2 cycle behind or negative 180 degrees of phase, we call that antiphase. Now, if it's between being in phase and in antiphase, we don't have a special term there, but that's kind of this middle case example where we lag by 1/3 of a cycle. So the peaks and the valleys don't line up at all. They're going to lag consistently, like in this example, 1/3 of a cycle behind.